All right, it's on.
Uh, uh, Welcome all again for another session of our book club. So I I, I believe like we on the in the third chapter we kind of covered LSM and SS tables pretty in depth in last couple of weeks. So I was thinking like we kind of started. I mean, like we talked about Bloom filters a little bit, uh, but we can get started with the performance of we can get started with the performance optimizations and move to btrees. So that's what I was thinking, unless anybody have any other questions left from our last week's discussions. So don't think so, right? Okay. So Bloom filters, I think Abhishek kind of showed us in the last week, like how the file structure is for different kinds of segments, Bloom filters, and all these things. So I'll just briefly tell like these Bloom filters are something that are specifically used to efficiently find out if a key is present or not present. So I was looking at some documentations. It's pretty straightforward. It's like they say the key is hashed. Uh, the key is hashed multiple times and stored it in a bit mask kind of way, like this bit mask kind of way, to find out if that particular key is present or not. It's not like it doesn't say exactly whether that is present or not. It gives a probability depending on the hashing algorithm that you use and the number of I think the number of this bits that you use. It kind of gives you the probability. It says for sure if there is a probability of if there is a probability of finding that key, uh, and it can also say it may be present. So but it's an efficient way to find out if the keys are not present. So Bloom filters is one of the optimizations that's available, that's used along with LSM trees. So another way, like we had talked about, like compaction on the segments that are created, right? So like the multiple segments that are created in the memory, and the author talked about like how the compaction is done. There are two types of compactions that he talked about briefly. That is like the size tied compaction and the level compaction. So uh, it did not explain a lot on that here. I'm assuming there may be more discussions about those things uh, in the later chapters. So this is what he gave, and it kind of made sense for me. I don't know if anybody else have more to add to them. Is there like the two levels where size tied, where newer and smaller SS tables are successively merged into older tables. So I'm assuming um, the uh, uh, compacting the smaller ones into bigger ones helps us in a way um, where we don't have to maintain multiple segments, is what I'm assuming. That way it helps it. There was not much of description there, so that's what my assumption is when I read through his optimization. And level compaction is where uh, the key range is split into small SS tables. Older data is moved into separate levels, which allows compaction to proceed much more incrementally. So, yeah. Anybody else have any observations on this? Since there was not much given in the book about these things.
Yeah, I would interest the level of compaction, not
Mhm.
really understand what that means and how to, implement it.
How to implement it?
Not implement, but the concept. How is it different than the side tier
Yeah,
compression?
yeah. Cited seem pretty straightforward, right? I mean, like compact the smaller ones, so that kind of allows not maintaining so many segments. Um, I don't know. Actually, I don't I don't have much into it because this is what was given in the book. Anybody else have anything else, or do we think like we should somebody should research more and talk about it in the next session?
Yeah, sure. I think I can look through it. I didn't have a chance to read through it, but I can definitely follow up on it.
Yeah. So Leon, that's a good question actually. I mean, like I didn't go research more into it. I've only looked at what the book had written, book has given. I was
Yeah.
assuming like they will discuss this more in detail in the later chapters or somewhere. So, and I believe that was the reason they did not cover a lot there.
I look at the index. There's no mention about that level of compassion. But reading from that, it's a split up. The key range in smaller table, right? And move the own data, own the data to the new one. This is different than the size tier, right? The size tier, we just move the new one to the old one, right? We keep merging the new segment to the old segment, So old segment get, kind of aggregate get bigger and bigger. But this one is different.
Yeah, let's follow up on it maybe next time. And some of us, any interesting things that you find, we can keep adding to that Google Doc, and then we can quickly have a review of it next time.
Okay. Yeah, I agree. I think it would not block us from moving forward because it's kind of an optimization. So we can definitely have a separate.
Yeah, it's not, but I just mentioned if somebody know, they can
Oh,
explain,
okay.
or we can move forward.
Yeah. That's what I was asking if anybody knows about it. More, anybody knows more about it. Looks like everybody are kind of on the same page and whatever the book has given. So
I can explain a few details. I mean, I am not uh, completely up to date on that.
mhm.
So basically, instead of in size, you merge it by size, similar sizes, SSTB files. So in levels, you actually move. So every level has a specific size. Uh, uh, I mean, uh, there are L0, L1, L2, L3, something like this, and there's a multiplication factor. So the size L0 is the one immediately that is written after when keys get flushed to the hard disk. Uh, from the RAM to that disk. But L1, L2, L3 are the levels that actually, uh, I mean, actually hold the data keys in the order. Basically, so you maintain the size of each level in a fixed limit. So if it exceeds a certain limit, you compact those keys and you push it to the lower level. So if level one is size, let's say 200 MB or something, and the multiplication factor is 10, so it would be 2000 MB, so 20,000 MB, like that. So whenever L0 files get pushed, the L0 files are, there can be overlap between any of the files. There can be multiple SSTB files in the L0, and there can be overlap between any of them. But when you come to L1, L2, L3, the overlap can be only, there will be no overlap as such, but there can be overlap between the L1, L2, L1, L2 or L2, L3, something like that. But there won't be any overlap between SSTB files in L1 itself. And these are a sorted range. So every SSTB file in suppose if a file occurs in L1, it will occur only in one SSTB file itself. So it tries to maintain that sorted range, and there is no overlap as such.
Oh, okay. But to maintain this,
yeah,
that's a good way, I think. But is there an overhead to maintain all these levels?
Is there an overhead as in how, in which way?
So to for the compaction to happen, right? The
Yeah,
compaction logic should know all these levels, right?
yeah,
Like
it,
what level?
yeah, go on, sorry.
Yeah, I mean, like who at what level are this maintained? I mean, like so far it was pretty straightforward. Like you have the oldest one, the newest new files, and old files are always compacted based on the size. And now with the introduction of levels, it also have to make sure of like the algorithm of like, because if it is in level 1 and level 2, uh,
Yeah,
the gates
the
are
thing
open.
in the thing in some size tiered versus level tiered is you are merging the similar size files in size tiered. So the key, I mean, there is no range. I mean, there can be overlap between any of them. So you need to search in every file in size tiered. But whereas in level tiered, I mean, there can be overlap in I mean, L0. L0 is an exception, but L1, L2, L3, it can occur only in one file. So if there are n levels, you accept L0, you need to check only n files.
Hmm.
So if you are maintaining only 4 levels, so you would need to check L0 plus four more files.
Interesting. Okay. Okay. So Uday, where was this? Are these details mentioned? Is it in the later
So
chapters in the book, or it's from your experience with
no,
it?
no, no. Yeah, actually, I have to work on some project related to RocksDB.
Oh,
So you can actually find these details in RocksDB or LevelDB GitHub page. So they explained in a better way how the level. I think LevelDB only. LevelDB is the one that actually came up with that level tiered compaction.
oh, okay. Interesting.
So yeah, so they explain it in a better way.
Okay. Okay. Probably I should go back and read more on it. Um, yeah.
Yeah, it's good information.
Yeah.
We only search a small subset of files, right? Like level one in level one level two, level three, and probably all in level 0.
Yeah,
Mhm.
and compaction is also tricky in level tiered. So basically, you can have simultaneous compactions in levels as well, and the size of the level increases in for each level. So I mean the amount of CPU consumed increase in the I mean in the level tiered as well. I mean, if you're compacting in the higher levels, it actually becomes, I mean, it becomes more CPU, I mean, intensive. I mean, because you are compacting large files.
Mhm. Mhm. Interesting.
So, yeah.
When you say compacting, that because the book also they say two different compacting, as part I understand. One is like to merge the record and to delete the duplicate one, but they also like compacting in terms of like you make the block size smaller, right? Like kind of really compaction, make the block size really smaller so that you can save the disk space and save the IO.
I
Uh,
think,
yeah, sorry, go on.
yeah, yeah. It was like not making it smaller, right? It was like one is like making it all like one fixed size that is decided on the segment and removing the duplicates.
Yeah,
Right?
that's one compaction, right? But the other one, on one of the page, he mentioned that it also like make the size of the block smaller, you know. So we save the IO and also save the disk space because we have the range key, right? We know the key, the pointer to the address, of one key, and the pointer to the address of the next key, and the block, the data between those key can be compact, make it smaller, right? So, you know, when you need to read it, you just uncompact it and read, you know, and look for the key value.
Are you referring to the
Compaction is different from compression. I mean, I'm
Oh, yeah,
not
yeah,
sure.
I mean, yeah, okay, yeah, I mean compression, yeah. Okay.
Okay, I think, are you referring to the btree's compression? Because
Oh
I,
no, I refer to this
oh,
you know, LSM file. You know, I can post the page number later. Keep
okay, sure. Okay, I think, thanks for that. I think that's helpful. Probably that's a good follow-up read to have like the level DB and understand more about the level compaction. So I think with that we can move to the next btree's topic, I believe, unless people have anything else on the performance optimizations that are available for LSM. Cool. Okay. Um, I think with btree's basically what the author is talking about is like the optimization. I mean, like it's also again the sorted keys is the key here, but the optimization is like the size of the data that is used to write onto the disk. Typically, the 4 KB size of blocks is easy to manage. So the size of this using that as a key, making an optimization in that way. And also, I was not quite sure how that is done, but in LSM we are always in a mode of append only, right? So like we always append, though the key might be present, we always tries to append to the end. But I think in btree's there is a way where like we kind of uh, not always append, but if something is present, key is present, we actually override the data which we already know is kind of a duplicate. So those are the major things that come with btrees. Um,
Yeah,
so that's what
like
I.
one of the things where we say like B trees is like a mutable data structure, and
Mhm.
the LSMs are more like immutable because we keep just.
Right.
Yeah.
Okay. So any other interesting things that you guys have found with btrees? I think there are like some more optimizations that are there, but basically that's what I understood. Like when I read through it, these are the two important things when we compare it with the LSMs.
Like for btree, if the block size is 4K byte, let's say I need mutable, and let's say we need to write, you know, modify it, write, you know, bigger than the previous size, then, you know, how does it work?
Yeah. So I don't know. Naga, were you going to
Yeah,
say?
go ahead. I think they give a specific example of like that could happen. They'll actually if they do it, they split it and update all the indexes on like how that is mapped. Go back to the parent and update the index saying that now it
Yeah,
is.
and before that, I think there is a point that Leon mentioned that we should clarify that when we say we have a 4K page, right? But that 4K page would have several nodes in it. A B-tree node is not a 4K thing, right? It's a node of a certain size, and now the 4K is more like the access mechanism, right? When you read from the disk, like you're reading a 4K page, in 4K block. So a single page can have multiple nodes, and like what Naga is saying further on, that if you want to add or delete or change anything, you're basically playing with nodes. You are either splitting nodes or adding nodes and all of that.
Yeah, but I mentioned about the value. You know, the key remain the same. You know, because we in this case we go ahead and modify the data, right? We
We do
modify the
modify.
value, right? So we modify the value. Let's see. You know, previously we allocate this much. You know, this space for the data, but now you know we modify. We add. You know, the
Yeah.
space is larger. Then
Yeah.
you know, how could the file you know the space because it all compact or maybe not that you know I don't understand.
Compaction is not like here we are talking about, right? So let's say you have one 4K page with a certain number of nodes, and then when you try to add more data, and let's say it goes to the next, block, like 4K block, more like you're adding another, nodes, then, it's the B tree, how it links nodes, right? It has nothing to do with, I'm not sure if I caught your
Yeah,
question.
but you know that's not the new data get inserted, right? The new data get inserted, then you know you can you know get more space. But let's say you know you suppose you have the existing data, right? And
Yeah.
this data is like let's say 8 byte, right? This a key and value is 8 byte. Now you go ahead and you change it and you make it become 16 byte,
No,
right?
that's not how.
The value
That's
you
not.
change become.
No, so the thing is, I think so. Okay. So there are there are two things that come to my mind from what you're saying. In B trees, there is this concept of intermediate nodes and leaf nodes, right? In general, in trees. And the data key and the actual value, right? Whatever the actual data is, only stored in the leaf nodes, which is kind of pointer to the actual data stored on the disk. On the B tree, on the root level or on the internal nodes, you're basically just having pointers, to like what's the next, where should I go next to get a certain amount of data. And when you get to the leaf level, that's where you have a pointer to the actual data, which is not a part of, B tree. It's a
Yeah, so in that pointer to data, right? Previously we point to that block of data that contain only 4 bytes. So now we expand that value to be 8 byte. Are we gonna allocate, you know, change that
but why
address
would
to a
we
new one?
why do you think we are going to change 4 byte to 8 byte? It's just an address, right?
No, the
No,
value.
we are not storing value, right?
Yeah, we are just storing address.
We are storing address to the actual data.
So the pages that we are creating is not for the data, but for the keys.
No,
Both
no, no. It's key and pointer.
key
That
and the pointer. Yeah.
right. So in the internal nodes, you have pointers to what is the node on the next level that I should go to. So think of it like 4-level tree, right? Last level is having a key and a pointer to the actual data, right? Somewhere on my disk. And all the 3 levels above. So you start from the root and you say, okay, where should I go next? Like, which node in the level 1 should I go to? So you go to the next, pointer will take you there,
Right.
so on. So that's just for getting to the right node on the leaf level.
Yeah, that's what I understand. The last level to leave is the one that store the data, right? But I'm saying, you know, unlike the previous LSM tree, you know, we can keep append data to it. So when we append data to it, the size, you know, of the value, you know, doesn't matter because we always, you know, write to it, right? So, you know, but here it allow us to modify the data.
Even last one is not value, my
The
understanding.
key value, right? Think
No,
about
the
the key.
value, by
Value
value,
can be the memory address, right?
yeah,
Of the
value can be
data.
the memory address or the disk address. Value is not the data actual. Value word is overloaded in a way, right? Value
But you can think it in simple term as a key and value, right? Now, you know, that's just think about, you know, the value is the actual data you want to store.
value is not the actual data here.
Yes, you can, but you can think of that, you know, because eventually you have to get to that memory address or, you know, get to that data, right?
Yeah, but that pointer will take you to the data that is not
Yes. So
tree.
so So let's say because you append only, so that data can be anywhere, right? I'm saying because of that, you append data only, so that data can be small, can be bigger, it can be anywhere. We don't restrict on the size. But on the btree right here, because we already have existing, we modify the data. And suppose the data is 4 byte, and next to that 4 byte, that's some other data, right? That belong to some other key. And now if we go and modify, you make the data bigger, right? You want from 4 byte, you start some string 4 byte to 8 byte. And I want to know, like, how would we be able to modify the value?
I think the 4K pages that we are talking about is the key, and the value. The value here is the address. It's not about the actual data that is present in that address. So that is maintained by the memory. I mean, like if you are trying to override, uh, if you are trying to append to that memory, and if that memory is, it need not be contiguous. Like if that memory is being used by something else, I believe that's a different mechanism of memory management, whether that will be moved to a different location, or like it will be linked somewhere.
Um,
I think that's a different thing altogether, right?
So let me, so what we can do is to keep the pace going. So maybe would it make sense that right now, these are good questions, right? How about, so I took the question before, level versus size tier. I think Uday explained, gave us a good idea, but we can, if anyone has more, we can add next time or add to the Google Doc. And now this question that Leon is sharing, maybe I'm not able to explain it correctly. I still feel that we are discussing the same question that Leon had earlier about, he is asking about, I go from 4 to 8 and it can conflict with my next key. Like, how do I handle that situation?
Okay, so I can give an example of database schema, right? When you define the database, like a SQL, your database schema, you have to define, okay, this column is the size of this column, the data type of it, right? You can say, okay, this type is
No, I
integer, and
understand.
then
I
4
understand.
byte. Yeah.
I understand your question, Leon.
Okay.
When you decide 4 bytes and when you
Yeah.
go 8 bytes, doesn't it cross the boundary there? And how
Yeah.
do you handle, like, the next data type that you have, next field you have?
So it's a simple. I have a simple answer, right? So it means that if we have a data which is more than 4 kilobytes, we cannot store in the B tree. Is it like that? It's not like that, right? It has to
Not
be.
like that.
I mean, it depends on the implementation, but it has to be that you are storing the memory reference. Otherwise, something which is more than 4 kilobytes, you cannot ever store that in the B tree. So
4 kilobytes is just a point of access, right? Like
yeah.
bit of access. Like 4K is the data. But I think we are again, maybe. Okay, Abhishek, I'll let you go. Sorry, I interrupted.
No. I'm just saying, yeah. I think let's keep on going. And
Yeah, and maybe we can, add more to it, what we think in the doc, and we can discuss offline. And then if still it's not clear, we can pick it up next time. If that makes sense to everyone.
yeah.
Sure. So, but just to one quick thing on it, I'm still confused on that part. Like the 4 kilobytes that we're talking about, right? That's the core of B tree, right? So
Exactly.
that's the core of B. I mean, like the core optimization is that, and not appending but overriding these values.
No,
So
overriding is fine, but I don't agree with the statement that 4K is a characteristic of B3.
uh, that's
This,
the
I think
this
yes,
is just
that's the
sorry.
This is a fixed size blocks. That's what it says.
sure.
At the very
Fixed is
beginning.
okay. Fixed is fine. I'm like, like it says 4KB or bigger, but we shouldn't really take that as the takeaway here, right? Like if we later on we want to discuss B3s, we shouldn't come up with saying, oh, it's a 4K thing. It's not like a number. There is a kind of a reasoning and how we interpret it. I think that's more important rather than saying fixed size, I agree, fixed size blocks or pages. But it's not something unique to btree.
But I think
So
that's the reason. Sorry,
no,
I
no,
think
go
that's
ahead.
a reason for it, right? Because btree is nothing but a whatever data structure like a binary tree or red black search tree or EVL trees kind of things. But now the problem is you need to persist on a disk, and
Yes.
when you persist on a disk, you need to optimize your speed of your process, right? So rather than going to a memory location, going to a disk location and reading just that node,
Yes.
which might be a
No, I agree with
byte.
that. Like 4K, that's why it's the reason, right? You want to optimize that at one shot. What is the block size you can read? You can read 4 KB, right, from a disk in one shot. So you want to optimize that. You don't want to read small chunks and keep going back to disk, right? That I agree. But I was just like, it's a very minor thing I was highlighting about fixed size, and the reason why we have 4K is important, but it can be applied to any other data structure also. It's not something unique to B3s, right? I mean, the idea is tied to, I want to minimize my disk reads and disk seeks, right? So I want to read it in the best atomic way, which is a 4 KB unit. But I can do any data structure.
No, I mean the file system is gonna give you 4K. You cannot say that just give me 1K, right? So
Yeah.
that's why they keep it. So if we write and create a new file system which can give us a block of 1 kilobyte, then we would keep it 1 kilobyte.
Yeah, correct.
Yeah.
Yeah.
Right.
I mean, like 4K, the specific 4K is tied because of the file system.
Yeah,
So
yeah.
those are the blocks that it can,
Yeah,
the
that's how I
CPU
mean.
can queue back faster. So that's how we are using this thing. Okay.
There is just one thing I want to highlight. It can be useful as a thing to keep in mind for interviews, right? The general concept here. We all talk about B trees, binary trees, right? In algorithms, that's pretty common. But the difference here, and with B trees, we talk about a branching factor, which is much more than, like 2 is minimal, but here we are taking example of 500, right? So, why? So this is more like an interesting thing to know, that why do you think a higher branching factor would help? What is the reason for B trees to follow a higher branching factor? I hope everyone is clear with that.
When you say high branching factor, the 500 branching factor.
Yeah. Like, why not? What is it that 500 is giving you that 2 it's not? If you try to do the same thing with a branching factor of 2, what is it that is, you're losing there?
You minimize the height of the tree so
Yeah.
that we go on a few nodes to reach the destination.
Yes, exactly. Right. So that's a critical factor in databases, right? Relational databases, B trees are used. You want to minimize how many, levels you want to reach. Yeah, just like a highlight of
Yeah.
Yeah.
Key is keeping the levels low. Right?
Yes.
And like based on that, the branching factor.
Yeah, branching factor defines the levels. Yeah. All right, let's move on.
Okay. Cool. I think you kind of covered the branching factor. I think that was the next part of it, and how this branching factor impacts and how much it can store. I think with 4 level and 500 branching factor, I think it's like 256 TB can be used. Okay. So it's like 256 TB of data can be referred with this kind of branching factor, right? It's like
Yeah, like the keys and the pointers together, right?
yeah.
Yeah.
Together can, so
Because
that
every
the
node is like a key and multiple pointers.
yeah. But this is like not the data that we are referring to, right? It's the
No,
So if
it's
you
the
take, like,
node, it's the node information, right?
yeah, yeah,
Because btree, when you're talking about btree size, you're talking about what's the space taken by all the nodes, right?
by all the indexes, index values, index and the memory locations.
Well, memory is not coming into picture here, right? This is
I'm
disk
saying
structure.
the
So,
address of memory,
sorry.
the address of the data, right?
Yeah,
Key and
address of the data and the key. Yeah, the key and the address.
yeah, yeah. So that
Is
means
that like 256 TB? Does it fit into one single machine? Oh,
I mean, it can, right? These days, storage is like crazy. You can have like, I mean, one machine can be tricky, but you can arrange
And
everything. Yeah.
and maybe he's saying that like just in 3-4 levels you can store
Yeah,
this much data, but it does not
exactly.
mean you have to store this much data.
Yeah, correct. That's true.
I was looking at this 256 TB as the in-memory thing, actually.
No, it's not in
that's
memory.
too big for in-memory.
Yeah,
Yeah. That's what it's too big for in-memory. So
and
because it,
B-trees are used for disk. Yeah.
yeah, because the B-tree has the 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 B-tree, the index and the memory locations is also stored in memory, right? Before it goes into these segments. So if this 256 is referring to the key and the value, which is the memory location, so that's also stored in memory. So this is referring to what can be in memory.
I doubt. I don't think this is like B-trees are not for, from what I know in relational databases, they are an index strategy for keeping data on disk. Like when you search data on disk, that also needs to be efficient. Like you can't have, first of all, in general, you can't have this kind of data in memory.
I
And
believe that OS cannot handle that to 56 TB. So 64-bit OS can handle 2 to the power 64.
and for sure, I mean, working on, that's what I know. Like B-trees are mainly used for disk indexing.
Oh, okay. So, but I'm a bit confused on that part because for all this indexing that we have, like in memory, we have, like if you look at LSM trees and all these things,
Right.
right? We have in memory, we have a structure that we maintain in memory,
Yes,
and then there are segments which are on the disk.
correct.
The AVL tree we talked about it's an in-memory thing, right?
Yes.
Now that got changed to a B
I mean,
tree.
I don't know how they are presenting it, but I know, I mean, we can check more, but like relational databases, that's like the bread and butter. Like B trees are used for storing data on disk. That's a common structure. But having said that, it's not like, if you think about the concept of B tree, you just have a simple tree structure with a branching factor. You can always have a B tree in memory also, right? It's not like you can't have a B tree in memory. So maybe I should put it that way. That it can be an in-memory data structure for sure, but in general, when we're talking about data storage and stuff, B trees are very popular in relational databases for storing data on disk.
Yeah. Okay.
So how does it search? Let's say if it's not in memory, let's say need to find a key, and how does it search? Does it search in memory or go to the file
No, so we
B-tree?
also have indexes even on disk, right? Like how do you optimize? You don't want to search through the whole B tree. So you build on indexes on top of it, which can help. And then you can pull that index, which is much smaller in size than the actual B tree. And you read that index in memory and you use that to, search through your actual disk structure. But maybe I'm jumping ahead. But that's the idea. I mean, B-tree is the full data structure, and then you build indexes on top of it. That is fair enough.
No, I think btree is what the index is, right? Because the table stays separate and indexes stays separate. Otherwise, if you drop an index, the table will get also deleted, right? So I think
No, not necessarily. First of all, that's not the case, right? What you're saying, when you drop an index, table gets deleted, you're talking about a very specific index, which is like a clustered index. But you can have secondary indexes, which are, of course, it won't make sense if, so you can independently drop an index without dropping the B tree actual structure. So those can be independent as well, depending on which index you're using. But so let me kind of just quickly rephrase some of the statements I made so that it might be confusing. So I'm saying that B trees can be in memory or disk, and we can make indexes, additional indexes, which are essentially B trees only, and we can have them in memory to have quick access to our disk structure. So yeah.
Okay. Cool. Okay. Thanks, TP. So I think we are little almost out of time. So let's stop here so that we can have some time to get ready for the next session, which starts in another 10 minutes. Just to, maybe we can stop recording.
Sure.